Hey there and welcome. Today we're diving deep into a concept that's right at the heart of the generative AI boom, transformer-based LLMs. If you've ever wondered how models like ChatGPT actually pull off what they do, well, you've come to the right place. Let's get into it.
All right, so let's kick things off with a bit of a puzzle. What on earth could a Rubik's Cube possibly have to do with artificial intelligence? I know it sounds a little random, but stick with me here, because this little cube is pretty much the key to unlocking how these crazy complex models actually work.
And that leads us right into our first section, the transformer analogy. We're going to use this really simple visual idea of a Rubik's Cube to get a handle on the core function of what a transformer model is all about.
Okay, so picture a scrambled Rubik's Cube, right? It's just this chaotic mess of colors, a jumble of data that has no real order. But then you apply a series of moves to transform that mess into a perfectly solved cube. Well, transformer models do the exact same thing, but with data. What makes them so powerful is their ability to see the entire jumble all at once, understanding how a word at the beginning of a super long sentence connects to a word way at the end, and then transforming it all into something that makes perfect sense.
Okay, so with that Rubik's Cube idea fresh in our minds, let's get into the more formal definition. And you'll see pretty quickly that the name itself tells us almost everything we need to know.
So here it is. The most important clue is right there in the name. A transformer-based large language model, or LLM, is built on what's called a transformer architecture. And its whole job, its entire purpose, is to transform an input, which it sees as these little pieces of data called tokens, into whatever output you're looking for, whether that's an answer, an image, or even a piece of music.
Let's strip this down to the absolute basics. If you walk away with just one thing, let it be this. These models take in data, they use these incredibly complex neural networks, which are basically digital brains, to find all the patterns and context, and then they spit out something that a human can actually understand. It's really that simple at its core.
Right, so we get what they do, but the big question is, how do they do it? Let's take a quick, high-level look at the process. And don't worry, we're not going to get bogged down in all the super technical jargon here, just the basic flow.
It's really just a simple three-step process. Think of it like this. First, you've got the input. The model gets fed a bunch of data, all broken down into those tokens we talked about. Second, the process. This is the magic part, where its neural network goes to work, figuring out how all those different tokens relate to each other. And finally, the output. It generates a result that's coherent and actually makes sense to us.
But here's where things get absolutely mind-blowing. That process step, the scale is just staggering. We're talking about models that have billions of parameters. You can think of these parameters as like billions and billions of tiny little knobs and dials that the model has learned to adjust perfectly during its training. The complexity is just vast.
And this brings us right back to where we started, doesn't it? After all that crazy complex stuff happening under the hood, billions of little dials being tuned just right, what comes out? A simple, organized, solved state. The final output is meaningful and coherent, just like that perfectly solved Rubik's Cube.
Okay, so theory is great and all, but where do we actually see these things in action? Let's switch gears from the abstract idea to some real-world examples that you probably use every single day.
Well, you've definitely heard of these two. You've got GPT-4, that T in GPT stands for transformer, by the way, and that's from OpenAI. And then there's BERT, a real powerhouse model that was developed by Google. Both of them are built on this exact same transformer architecture we've been talking about.
And here's a really cool thing about these models. They're not just a one-trick pony. They can be fine-tuned. It's kind of like taking a super smart doctor who knows everything about general medicine and then giving them specialized training to become, say, a top-tier brain surgeon. The model gets specialized for a very specific job, which makes it an incredibly versatile tool. And because you can fine-tune them, the list of what they can do is just huge. You've got the basics, like text generation, translation, and summarizing long articles. Then there's more creative stuff like writing stories. And of course, they're the brains behind the chatbots and virtual assistants we talk to, and it can even write computer code from scratch.
All right, we have covered a ton of ground. So let's boil it all down to the one core idea. If you're studying for a test or just want the key takeaway, this is the sentence you need to remember.
Here it is, plain and simple. Transformer-based LLMs process input data using neural networks to generate a human-understandable output, and they can handle massive datasets. Yep, that one sentence, it's the whole shebang. It perfectly captures everything we've just talked about.
So, I want to leave you with this question. We've seen how these models can transform a jumble of data into coherent text and summaries and even code. So it really makes you wonder, right? What are they going to transform next? Whole industries, the way we think about creativity, maybe even the way we interact with information itself. Definitely something to think about. Thanks for tuning in.